Hi, we continue the 11.8 model diagnostics. The model diagnostics are not just plots. Sometimes, often we have the numerical diagnostics needed. And the multicollinearity is the most common, the numeric problem in model diagnostics for linear model. So if the multiple predictors are almost linearly dependent, then the standard errors of the coefficients beta I becomes large. So the situation is like this. So suppose that you are walking two dogs together. And I'm not good at the drawing, but the two dogs together. And you pull the leash. And suppose that the two dogs pull the leash almost the same direction, but slightly different, maybe almost the same direction. Then you feel just the entire force. So if this is the vector A and this is vector B, then you can only feel A plus B. And it's really hard to decompose which dog is, how strong each of the dogs are. So this situation happens in a linear regression also. So think about y is equal to beta naught plus beta 1 x1 plus beta 2 x2 plus epsilon. And suppose that the x1 and x2 are really close, that we have really high correlation such as 0.99. Then it's really difficult to estimate the beta 1 and beta 2. It's the same situation. So the standard error of beta 1 and beta 2 gets very large, even though xy, x1, and x2 are true predictors for y. And how to solve this issue? Actually, for prediction purpose, the multicollinearity is not a big problem because the predicted value may be stable even if each coefficient is unstable. So suppose that x1 and x2 are almost the same value. Then think about the two cases. The beta 1 is equal to 0.5, beta 1 hat is equal to 0.5, and beta 2 is equal to 1.5. And another case, maybe beta 1 is equal to even the 2.1, and the beta 2 is equal to negative 0.1. Okay, so two models are totally different. But if x1 and x2 are similar, the y hat, the fitted values are almost the same. You can see if x1 and x2 are almost the same, if x1 and x2 are almost the same, then the 0.5 x1 times 1.5 x2. So this is almost the 2 times x1. And 2.1 times x1 plus negative 0.1 times x2. This is almost the 2 times x1 also. So actually, the estimate doesn't really matter. So the linear regression just minimizes the sum of residual squares. So it's not really important what the beta 1 and beta 2 are. So they just ignore it. So that is one possible issue. But sometimes we really want to know how much effect the x1 has on y or x2 has on y. So in such a case, the multicollinearity is a problem. So yeah, basically I explained the basic concepts, but we do simulation to clarify what really happens, what actually happens. So suppose that the true model is y is equal to 3 plus x1 plus x2 plus epsilon. And we want to simulate this several times, the 50 times. Then what we will see, that what will happen to estimate these numbers, the 3 and 1 and 1. So at first, the simulation setting, so we just generate x1. So it doesn't have to be random, but just we want to use the 50 different numbers. So just for that purpose, we generate the random numbers. And we define x2 as x1 plus 0.3 times the random number. So this means the x2 is very similar to x1. 0.3 is small, so the x2 is just x1 plus some noise. Then correlation coefficient is almost, between x1 and x2 is almost 0.95. Then we define y as the 3 plus x1 plus x2 plus the random normal, the 50. So this is the true model. So now we generated the data x1, x2, and y. And just ignore other part, and we estimate this model from just the data y, x1, and x2. Then see what happens. So this is the result when we fit y on x1 plus x2, and the x1, the coefficient of x1 is 0.72, coefficient for x2 is 0.93. Okay, intercept is anyway fine, and the true numbers are 311. And okay, so it's kind of reasonable. So that's slightly off, but anyway, we only have 50 observations, so not a very reliable estimate. But the problem is that even this is the simulated data, and the x1 and x2 surely the affects y, but still the standard errors are very large. Not that huge, but at least the standard error is large enough to make these coefficients insignificant. So even though the true model and 50 observations, still that we cannot really detect the significant difference from 0 for beta 1 and beta 2. So that is a problem. So how to deal with it? Maybe the one solution is we only fit y on x1. Then we only have the one predictor and the no similar predictors. So we don't have any trouble. And x1 is estimated as 1.61. So this is almost the summation of the two coefficients in the previous slide. Then standard error gets much smaller because we don't have any identification problem of x1's coefficient and x2's coefficient. So t-value becomes very significant, and we can show that the x1 is significant predictor to explain why. Also, we can fit the y on x2. So the situation is similar. So estimate for the coefficient of x2 is 1.62, almost the same, and the standard deviation 0.165. This is almost the same, and the t-value very large, 9.8, and this is very significant. So we can surely say that the x2 explains why. So which model we should use? Okay, so sometimes we tend to use the second or third model because we can show the significance and the result is clear. But not necessarily that we have to use this model. So the true model is not necessarily worse than the alternative, this model. Because, for example, if we compare the adjusted R square, actually true model is slightly better. Okay, we can go back. Adjusted R square, if we only use x2, 0.6599, 0.6509. But if we fit the both, then actually 0.666. So it's slightly better. So it isn't really worse. Just the identification problem makes it difficult to have the significant predictors, but still it's fine. But standard error just becomes large. So don't be surprised if you fit y on many seemingly useful predictors and that you have no significant variables. And now that we consider what's the best way to solve this multiple collinearity, especially if you are the biologist or economist, you want to show that some specific variable affects y. So some possible remedies. So one is principal component analysis. So idea is that okay, so x1 and x2 are so similar, so we cannot distinguish. So think about some composite index, such as maybe just the average of two variables. Then we only have to use one variable, and still we can use a kind of combined information of x1 and x2. So if you fit y on x bar, probably the result is better than just fitting y on x1. And another way is the penalized likelihood method. So this method is actually penalize the large parameters. So y is equal to beta naught plus beta 1 x plus x1 plus beta 2 x2. And if beta 1 and usually the criterion is just to minimize this epsilon, size of epsilon. But the penalized likelihood also penalizes the size of beta 1 and beta 2. So in terms of likelihood function, that we use the negative log, the likelihood function, sorry, the maximized likelihood function, so minimize negative log of likelihood function. But the penalized method, they have another term, R of theta. R of theta is typically summation of absolute value of theta I. Then we minimize the entire quantity. So we wanna maximize likelihood at the same time we wanna minimize the size of the estimated parameters. Then we get some reasonable estimate. So we will not get very large beta 2. So this method is useful, especially when the beta 1 and beta 2 are unusually large. So in the previous example, the true beta 1 is 1, true beta 2 is 1, but if estimated model is y is equal to 2.9 plus, for example, 5 times x1 minus 4 times x2, maybe 3 times x2, then it's certainly a problem. And if we use penalized method, then we can make these estimated parameters much smaller and much more reasonable. Yeah. And this kind of multicollinearity problem always happens if P is too large. So suppose that the sample size n is smaller than the number of predictors. Then actually, you can imagine that we have more predictors than observations. So we can explain everything, and still we have some freedom to determine the estimated parameters, coefficients. So this case, we always have to use some method such as penalized likelihood. And this is actually the common problem. So think about diagnose some image data by medical doctors to see the malignancy of the cancer patient. Then image 100 by 100 pixel image is basically the 100 times 100, so 10,000 dimensional variables. So we have x1 to x sub the 10,000. But often doctor can diagnose images after doing the training to see maybe just 100 pictures. So that means n is 100 and p is the 10,000. So it's common that p is much larger than n. In such a case, this penalized method should be used statistically. So medical doctors do penalized the likelihood methods in their brains. Yeah, so these are the overview of multicollinearity. So multicollinearity may not be a problem if your objective is just forecasting. But for interpretation, if you put too many variables, it has some trouble to interpret it. And there are some ways to solve multicollinearity. And we don't cover these, but there are several statistical methods. So this will be covered in the statistics, the 5820.